Why don't we get started? If people want to turn on the camera again, or willing to do that, would be great. Just to create sort of class atmosphere as the best as we can. Okay, so this is going to talk today about this paper, the benefits and cost of writing a Unix kernel in a high-level language. This is basically a paper that was partly written because of S081 or H08. This is a paper that we've written, Robert and I, and but the main person was the main lead author was Cody Cutler, who TA'd this class many times. It's always a little bit, I don't really enjoy actually particularly talking about papers that we worked on ourselves, but this paper came about basically of 081 and 828, and so I'm going to use some slides this time instead of actually writing on a whiteboard. And so really the source of this paper is this question, in what language should you write a kernel? And this is a question that many of you asked, or your students in the past, 828 or S08, asked it many times. Partly because you have bugs in the operating system or in your kernel, and you're like, well, if I would have written in this other language, then maybe I would have not had those bugs. And so this is a question that often comes about, and it turns out, in the operating system community at large, this is a sort of a hotly debated question, but not that many facts to actually make a sort of any informed discussion. And what we'll see at the end of this lecture, or during this lecture, or as you read the paper, we don't really have a crisp answer to this question. But we have sort of this paper contributes a bunch of data that allows you to have a sort of a little bit more of an in-depth discussion about what is a good programming language for the kernel. And so that was really the origin of this paper, and so we're the source of this paper is basically you guys. Try to answer this question. We wrote a new kernel, and we did it in a language with automatic memory management. That means with a garbage collector, so you don't actually have to call free, and that avoids a class of bugs. So that's one of the properties that a high-level language typically has. And so we wanted to have we picked a language that has that, and we followed basically the traditional monolithic Unix organization so that we could do a sort of a fair comparison. And in fact, in some ways, you can think about what we built is something like x86, much more features and more high performance. I mean, as you know, x86 has all kinds of quadratic algorithms or linear search type algorithms, and of course, if you want to achieve high performance, you can't have those. So that was the origin of this paper, and the origin why we built Biscuit, trying to answer that question, or at least shed some light. So I'm first going to talk a little bit about sort of more general background, give a lot of questions over email, or sort of trying to get a little bit more context, and then we'll dive into Biscuit in more detail. And feel free to jump in, with questions in any particular point in time. As I said, this paper was motivated, by questions that you asked, and so please keep asking questions. As you just to sort of the setting of this paper is that a lot of kernels are written in C, and x86 is written in C. You're programming in C, but most popular kernels that sit on your desktop or your phone are written in C. Windows, Linux, all the various forms of BSDs. And the reason they are written in C is that C provides you a lot of control, as you've seen in the labs. You have complete control over memory allocation and freeing. There's almost no implicit code. You can almost sort of imagine when you're reading the C code, like what the corresponding RISC-V instructions are. You have direct access memory. You can read and write, the PTE bits, or the registers of devices. And C itself, there comes with very few dependencies. There's no large runtime that you actually have to to be able to run a C program. You can almost run it almost immediately on the bare hardware. And you've seen that, like when x86 boots, there's basically a few lines of assembly, and then basically you're running C code. So there are all the sort of good virtues of C, and one reason that we like C a lot. But C also has some downsides. It has been proven over the last sort of decades that writing secure C code is difficult. There are types of bugs that can often be exploited, whether it is buffer overruns, which are probably the most well-known one, like you're writing behind the past an array bound, or you're writing below your stack. Use after free bugs, where you freed some memory, but it's still in use. And so somebody scribbles on it, and you may scribble something bad on it. And generally, when threads are sharing memory, it's typically difficult to decide, when actually the memory can be freed. Some of these bugs, don't really show up that. Some of these bugs manifest themselves explicitly in XV6, some less so. XV6 is very little dynamic memory allocation. Almost everything is sort of pre-allocated right up front. But buffer overruns and use after free bugs, definitely do show up. And so, in fact, if you look at CVEs, these are the, there's a website, or there's an organization that keeps sort of control, that checks and keeps a record of all sort of the security exploits. And you investigate that, you'll find that in 2017, when we were doing this paper, that there were 40 Linux kernel bugs that can actually lead to an attacker running, taking complete control over the machine. And clearly, those are serious bugs, and those bugs came out of buffer overruns and other type of memory safety bugs. So that's sort of too bad. That if you write code in C, that actually is hard, even for people that do this professionally, and to actually get this right. And of course, I'm sure you've seen this in the lab. Probably. Certainly, I remember from some of the Piazza questions, that a number of you run into this use after free bugs, in particular in the copy and write lab. They showed up a bunch of times. So, so one reason that a high-level language would be attractive is that high-level language, provides memory safety, and so all these bugs, or the CVE exploits that I mentioned on the previous slide, would just not be possible. Could just if they happen, they either would result in a panic, because the runtime would say like, oh, you're writing past the rate, you can't do that, or they just they couldn't manifest itself at all, because the languages wouldn't allow you to write that kind of code. So there are, of course, other benefits to a high-level language, which often is also mentioned, by students in this class when they're doing the labs. In addition to type safety, there's the automatic memory management of your garbage collector. So freeing is easy; you just don't have to think about it. The garbage collector does all the work for you. It's good for concurrency. It has good abstractions. Whether it's like in Go, it's interfaces, or some other classes, or some other form of that forces you or encourages you to actually write modular code. The downsides, and you might be wondering, like, well, if there's so many upsides to high-level languages, why not? Why is XV6 not written in Java, Go, Python, or whatever? And the reason is, or Linux, the reason is there's poor performance. There's a cost, to actually high-level language. Sometimes this is referred to as the high-level language tax. And these are basically, if you do an array bound, an array index, you have to check the bounds. You have to check null pointers. You have to have more expensive casts. And garbage collection itself is also not free. There's going to be some cycles spent, tracking down which objects are free and which are allocated, and that's the cost. So that's sort of from the performance side, and a lot of the paper focuses on this. And then in principle, often it's perceived that there's sort of incompatibilities with Linux, with kernel programming. No direct memory access, because that in principle could, violate type safety. No handwritten assembly. You need some handwritten assembly in a kernel. Whether it's the context switch between two threads, or like to get off the ground when the machine boots. Often, the language may have a particular plan for concurrency or parallelism that might not line up, with the plan that the kernel needs for concurrency and parallelism. We've seen, for example, in the scheduling lecture, one thread passes a lock to another thread, or there's sort of a couple, there's patterns of concurrency management that are sort of unusual in user programs, but that do show up in kernels. And so the goal basically of this paper was to sort of measure the high-level language trade-offs, explore the total effects of using high-level language instead of C, both in terms of safety and programmability, but also for performance cost. And of course, if you'd like to do this, this kind of an experiment, you need to do that sort of on a production grade kernel. You can't do that on x86 because it's so slow that basically you probably wouldn't learn anything. If the kernel's written in slow in C, you're written in slow in Go, it doesn't really tell you much about, the C versus Go question. It just says like, well, x86 is slow. And so you want to look to do that in a more, high performance, oriented kernel, or the kernel is designed for high performance. And so, one of the things that are surprising, because like many of you asked this, or your predecessors asked this, and you would imagine, well, this question must be answered in the literature. And, that turns out that actually isn't. It is, there's quite a number of studies that look into the question of like high-level language trade-offs in the context of user programs. But, as you know, the kernel is, quite a bit different from user programs. So, for example, memory management, careful memory management is really important. There's different types of concurrency may be slightly different. So we wanted to do it in the context of a kernel. And, we couldn't actually really find any sort of papers that really answer this question. The closest you could come to is there are many kernels written in high-level language. There's a long history of doing that, dating back even to sort of the early Lisp machines. But many of the sort of recent versions of these kernels are not really written with the idea of evaluating this high-level language tax question, but really to explore new OS designs or new OS architectures. And so none of them sort of really measure directly, sort of do a head-to-head comparison and keep the structure the same, so that you can really focus on this issue of the language as opposed to some other issues. In fact, we used to read some of these papers actually in the past. It turns out one reason maybe that there's not a ton of work that actually answers this, or a ton of papers that answer this question is it's actually tricky to do it. Basically, if you really do it right, you want to compare with a production grade C kernel. That means like something like Linux or something like Windows or whatever. But then you have to build a production grade kernel, and clearly for a small team that's very hard to do. There's lots and lots of Linux kernel developers. They make many changes, week by week, day by day, and so it's going to be hard to to do the same thing and build an equivalent type of thing. So you have to settle for something slightly less than doing so. So the best we could do, or the best we could come up to do, is build a high-level build a kernel in a high-level language. Keep most of the important aspects the same as Linux. Optimize the performance roughly. Optimize the performance until it's roughly similar to Linux. Even though maybe it's not exactly identical features, but gets into the same ballpark. And then measure the high-level language trade-offs. And of course, the risk, this approach is that, the kernel that we built, actually is slightly different than Linux. It's not going to be exactly like Linux. And so, you gotta be very careful when drawing any conclusions. And, and this is one reason why you can't sort of give a really crystal clear answer to this question that basically this paper poses. But we can hopefully, get a little bit more deeper insight than basically, saying almost nothing about it. Does this make sense so far? Any questions? That's sort of the context, of this paper, and why we went extra off and did it. Okay, so If there are no questions, I'd like to talk a little bit more about the methodology. So basically, the sort of setup is, here's on the left side, we have our, this is going to be, Biscuit. We're going to, in our particular case, we wrote for this paper, we wrote a kernel in Go. It provides roughly a similar, subset of the system calls that Linux provides, but the way to, but they have the same arguments, the same calling conventions, and we run basically the same applications on top of that interface. So one of the applications is NGX, which is a web server, and so the idea is that we run the same application both on Biscuit and Linux. The application will generate the same system call trace with exactly the same arguments, and both Biscuit and Linux, perform all the necessary operations that are invoked by those system calls, and then we can sort of look at the differences basically between the high-level language kernel and Linux, and sort of talk about like what are the trade-offs. So that's sort of the core of the methodology. And again, because Linux and Biscuit are not going to be exactly identical, there's going to be some differences, but we spend a lot of time in Biscuit trying to make the comparison as fair as possible, or as fair as possible as we could think of making it. So a lot of you asked this question, which high-level language should you use for this kind of work, and we picked Go, and for a couple of reasons. It is a statically compiled language, so unlike Python, there's no interpreter, and the reason that we like statically compiled, because that basically compiles actually high-performance code. In fact, the particular Go compiler is pretty good. So basically, it's sort of a high-performance language. Furthermore, the Go designer is actually intended it for systems programming, and kernels are a form of systems programming, so that seems a good match. And so, for example, aspect that why it's so good for system programming, it's actually easy to call assembly or other foreign code. It has good support for concurrency, quite flexible. And then the other reason that we wanted to use it is because it has a garbage collector. So like one of the things that you think about a high-level language, and one of the virtues of a high-level language is that you don't have to do memory management, and the garbage collector is typically in a central role in the provides a central role in that sort of memory management story. By the time we started this paper, or we started this project, Rust was not very popular, or Rust was actually not very stable or mature at that point, that you actually could write a real kernel in it. In retrospect, now we would do it again. You may would write it in Rust because it's also designed for systems programming. It has a small runtime. It produces good code. Although one thing that actually may still make it very interesting to go for Go is that Rust sort of takes the starting assumption that that if you want to high performance systems programs, then you can't do that with a garbage collector. And in fact, the Rust type system is set up in a very clever way and in a very interesting way, so that actually a garbage collector is not necessary. And in some ways, we really were interested in answering this question, like what is the cost of garbage collection in a high-level language, on kernel programming, and it's really impossible to use what is that cost? And in some ways, sort of Rust sidestepped that question and just like, here's a language without garbage collection. You have to think about this particular cost. Any questions about this in terms of the programming language we decided to use? Lots of email questions related to this topic. So,
yes, this is a theoretical question that maybe doesn't have an immediate answer. But if the Linux kernel were to be written in Rust, not Go, and like optimized in the same capacity, would it be able to achieve higher performance
than the Go kernel?
Than C, like a Linux C kernel?
I doubt it would be okay. Hard to just speculation, correct? Because we haven't done this experiment. My sense is, it would be not higher performance than C, but probably roughly in the same ballpark. because I C is so low level, you can presume whatever you would do in Rust, you could also have done in C. Does that make sense?
Yes, thank you.
Okay. Okay, so let's move on then. Unless there are any other further questions about this. And again, feel free to interrupt. And this is a bit of a discussion-based lecture. And so I would, it was intended to sort of stimulate intellectual interest. And so jump in if you have anything to think about this topic. So actually, before maybe a question I want to ask, maybe I'll come back to that at the end of the lecture, closer to the end of the lecture. Partly, the whole reason we want to use a high-level language is to avoid certain class of bugs. And one question you should ask yourself: were there bugs, in the labs that you had that would have been avoided if you had a high-level language? So think back. I'm sure you can come up with some bugs that cost you a lot of time and a lot of pain. And you could ask yourself for those kind of bugs, if the XV6 were written in the labs, were be done in another high-level programming language, would life be a lot easier? Would you have had a lot more spare time to do other things? So let's keep that question in your head, and we'll hopefully return to that at the end of the lecture. But if you have opinions right away, that's fine too. Okay, so let me talk a little bit about Biscuit and how it sort of works. And sort of the surprises or the things that we ran into while building Biscuit, things that we anticipated and some things that we actually did not anticipate. So the user programs, there's a classic kernel, monolithic kernel in the same way that Linux or XV6 is. And so there's user space and there's kernel space. User space programs are, whatever, it's your compiler, GCC, or in this particular paper, it's mostly a web server and some other benchmarks. And the user programs are actually all written in C, although it could be principal in any language, but since they're just the benchmark, we took C versions. And most of the programs are multi-threaded. So unlike in XV6, where basically there's one thread per user program, in Biscuit, actually, you support multiple user level threads. And for every user level thread, there's a corresponding kernel thread in the kernel. And these kernel threads are actually implemented by Go itself. And Go calls these Go routines. But you can think about Go routines just as ordinary threads, in the same way that XV6 has, and the kernel has threads. The Go routines are sort of similar. The main difference, correctly, is that in XV6, the threads are implemented by the kernel itself. And in this case, the Go runtime basically provides them. So the Go runtime schedules them. Go runtime has support for things like sleep and wake up or condition variables. They're slightly different than sleep and wake up, but there's some condition variable synchronization mechanism. And there's a whole bunch of other things, primitives in the Go runtime, and it's just provided by the Go language itself, and those have not been implemented by Biscuit itself. We just get them from the Go runtime. The Go runtime itself runs directly on the bare hardware. And I'll talk a little bit about that more in the lecture. But so you think about this as the machine boots, the first thing it actually boots is the Go runtime. And that causes a little bit of complications because, of course, Go runtime normally runs in user space as a user level program and assumes that there's a kernel there for it can ask some services. So, for example, it needs to allocate memory for its heap. And so there's a little bit of, so I'll talk a little bit about that. There's a little bit of shim code that the Biscuit has to basically trick the Go runtime into believing that it runs on top of the operating system, even though it's running on the bare hardware, and basically get it to boot. And then the kernel itself, it's very similar. You just think XV6. I think that's a good model, except it's a little bit more elaborate and more high performance. It has a virtual memory system. That, for example, implements mmap. The lab that you're doing this week. It has a file system, except it's a more high performance file system. It has a couple of drivers. It has a disk driver. It has a network driver. It has a network stack. So a little bit more complete. And the way you can see that is. It has 58 system calls, and I don't know, can't remember how much XV6 has, but it's probably in the order of 18, 19 or something like that. And the total number of lines of code is 28,000. And XV6 is like not in, I think below 10,000. So there's more features. Any questions about sort of this high-level overview?
Oh, sorry. I wanted to ask about the interface. So the interface is just like in XV6, right? So like the processes, they have to put something in some register,
Yeah.
and then they call the equal or whatever it is.
Yeah. I'll talk a little bit more about this, but it's exactly the same. Like there's no difference.
Okay, I see. Thank you.
So some of the features, I already mentioned them a little bit, but maybe worth talking about. So it's multi-core. Go has good support for concurrency, and so the Biscuit is multi-core in the same way that XV6 sort of has at least limited support for multi-core. In Biscuit, we have a little bit more fine-grained synchronization or coordination than actually in XV6. And it has threads, user-level threads, backed up by kernel threads. Which XV6 doesn't have. And there's a journal file system, a much higher performance. Think, you recall the ext3 paper. It's sort of like, the ext3 journaling file system. It has, quite, reasonable sophisticated virtual memory system, using VMAs, and, it can support mmap and all that stuff. It has a complete TCP/IP stack, good enough to actually talk to other, network servers across the internet. And it has 2 drivers with high performance drivers, so like a 10 gigabit NIC. In the next lab, you can actually implement a little driver for a very, very simple NIC. This is a much more high performance and sophisticated driver, and a pretty sophisticated disk driver. More sophisticated than the VirtIO disk driver that you've sort of seen or you might have looked at in the labs. Screen. So in terms of the user programs, as I mentioned before, every user program runs with its own page table. User kernel memory is isolated by hardware, so there's a user kernel bit basically. And every user thread has a corresponding kernel thread, so that, for example, when a user thread makes a system call, it will continue running on the corresponding kernel thread. And if the system call blocks, then another user thread in the same address space, and the user address space might actually be scheduled by the kernel. And as I mentioned earlier, kernel threads are provided by the Go runtime, and so they're just Go routines. So if you write if you ever written a user level application in Go and you're using Go and you use the Go call to create a thread, those Go routines are the ones that were actually being used by the Biscuit kernel. So talking about system calls, this question that was just asked. So it works exactly as roughly, as in XV6. The user thread puts in arguments in the registers using a little library, that provides a system call interface. Then the user threads execute a sysenter call. This Biscuit runs on an x86 processor, not on the RISC processor. So the assembly instructions for actually entering their system kernel are slightly different than on the RISC-V. But it's roughly similar to the RISC-V. And then the control passes to the kernel thread that was running that user thread, and then the kernel thread executes the system call and then returns using sysexit. So roughly similar thing. There's a trap frame that's being built and all that kind of stuff. Okay. Any questions so far before I dive into sort of the more sort of things that were unexpected or expected, but were a little bit more challenging than or different than things would go than in XV6?
I have a question. I think Go wants you to use channels more than mutual locks, I guess. So
Yeah.
would the design of some things in XV6 be used as channels instead of holding a lock for something?
Yeah, so this is great. Great question. So I'll come back to it a little bit at the end, further down, and we have some slides about what features of Go did we use in Biscuit. But in the end, actually, we didn't end up using channels that much. We mostly used locks and condition variables. So in some sense, closer to like the way XV6 looks than actually you would do with channels. We did experiment actually with designs of the file system that were much more channel heavy, but it didn't work out that great. We got bad performance, and so yeah, we switched back to sort of more sort of similar style of synchronization as XV6 does, or Linux uses. Okay, so there were a couple sort of little puzzles or implementation challenges as we went through. One, we got to get the runtime to work on the bare metal, and the required. We wanted to make, of course, like 0 modifications to the runtime, or as little as possible, so that Go come out with a new version of the runtime, we could just use it. And in fact, through the years, that we worked on this, or the Cody worked on this, we upgraded the runtime many, number of times. And that turned out to be a good thing, and it turned out not to be too difficult to actually to get it to work on the bare metal. Go in general is designed pretty carefully to sort of be mostly OS agnostic, because they want to be able to run in many operating systems, so it doesn't rely on a ton of OS features. And we basically emulated the features that actually needed it. And mostly, those were the features that actually just get off for the Go runtime to get started. And once it's started, it runs just happily. We had to sort of arrange the Go routine to run different applications. Normally in Go program, correct, it's all one single application, and here now we're using Go routines to actually run different user applications, but these user applications have to run with different page tables. And the little wrinkle here is that we don't control, or Biscuit doesn't control the scheduler, because we're using the Go runtime unmodified, so we're using the Go runtime scheduler, and so in the scheduler we can't switch page tables. And so what XV6 basically what Biscuit does is very similar to XV6. It actually switches page tables when it changes from kernel to user space, or the other way around. So when an entry and exit of the kernel, we switch page tables. And that means, like in XV6, and then when you need to copy data from user space to kernel space, or the other way around, you have to do that sort of using those copy in and copy out functions that we also have in XV6. Basically, you do the page table walking software. Another sort of challenge, or little challenge, was the device interrupts. And like Go normally runs in user mode, doesn't really get interrupts from the hardware. But we're using it on the bare metal, and so we're going to get interrupts. Time clock interrupts, interrupts from the network driver, interrupts from the disk driver, etc. From the UART, and so we need to deal with that. And there's also no notion in Go, for sort of switching off interrupts like while holding a lock, because it just doesn't show up in user applications. And so we have to be a little bit careful with how to actually write device interrupt. And basically the way we did it is we do almost nothing in the device interrupt. We don't take any locks out. Basically, we don't allocate any memory. The only thing we do is basically sending a flag somewhere that there was an interrupt, and then wake up a really functional Go routine to actually deal with the interrupt. And that Go routine, of course, can use all the Go features that it wants, because it doesn't run in the context of an interrupt handler, it just runs in the context of a normal Go routine. Then one thing that surprises was a bit more of a surprise. The first three things we completely anticipated that we would have to deal with when building Biscuit. The hardest one that actually surprised us, and we learned a lot about, was this puzzle of the heap exhaustion. So I'm going to talk mostly for a little while about heap exhaustion and what it is, how it comes about, and how we solved it. But maybe before diving into that, any questions so far? So crystal clear. Okay, so let's talk a little bit about heap exhaustion. I'm not going to go in full depth as in the paper, but at least to give you the flavor of what the problem is. So heap exhaustion, let's say the blue box here is the kernel again. And the kernel has a heap from which it allocates dynamically memory. In x86, we don't have such a heap because we don't have a memory allocator in the kernel. Everything's statically allocated. But any other kernel will have a heap so that you can call malloc and free in the kernel. And the things that actually get allocated on the heap are, for example, socket objects or file descriptor objects or process objects, like struct proc, struct fd, all the structures that we basically statically allocate in the x86. Normal kernels, they dynamically allocate them. So when you open a new file descriptor, there will be a file descriptor object allocated in the heap. And so then the problem is, like, if you're running many applications, they might open many file descriptors, may have many sockets, and they sort of start filling the heap basically slowly. And so, and the issue is that at some point, like, the heap is full. There's no space anymore for allocating a new object. So when an application asks, for example, opens a new file descriptor and there's like no, a new process, like there's new fork, and the kernel wants to allocate a struct proc in the heap, just like there's no space anymore. And what do you do then? What is the, how do you deal with that particular case? And this is typically, this is, maybe in common cases doesn't show up that often, but like if you're pushing machines hard, you may have, a couple of heavy consumer processes running user level processes, you might end in this situation where basically, all the available memory is just in use and your heap is just full. And no process is calling me free yet, because they're all running and trying to allocate more, resources for their particular jobs. And so all kernels face this problem, whether it's like a C kernel or a Biscuit or anything, and any kernel must solve this particular problem. The reason they sort of showed up for us as a serious issue in Biscuit was because in many kernels, you can return an error on a malloc. In fact, x86 does that, correct, once in a while. But in the Go runtime, when you call new to allocate a Go object, there's no error condition. New succeeds, and so there's no way to fail it. So let's talk a little bit about possible ways to solve this problem. We've seen it actually in x86 once in a while. Like if you remember the B cache, if x86 can't find a new block, a free block to use, to store a disk block in, and actually sometimes it just panics. Now this clearly is a completely undesirable solution, and it's not a real solution. So here's like why we call it the strawman solution. The other sort of strawman solution is to, when you call, let's say you allocate a new piece of memory, you go to call alloc, or new to actually allocate it. You could actually, wait for memory in the allocator. I'm going to be one proposal to do it. It turns out not to be a good proposal. And the reason it is not a good proposal is that you may deadlock, assume the following scenario, you're holding some, let's say the kernel has one big kernel lock. And you call malloc, you wait into the memory allocator, then basically no other process can run. And you would have a sort of deadlock type. Any next process that would actually try to run, for example, to free some memory, couldn't run and actually would deadlock. Now, of course, this is if you have a big kernel lock, that is an obvious problem, but even if you have a very small, fine-grained locking, it's easy to run in a situation where basically the person or the process that's waiting in the allocator is holding some lock that somebody else needs to actually free the memory. And that can get you basically in this deadlock situation. And so, strawman free is to basically fail, or when there's no memory anymore, alloc just returns like a null pointer. You check with the null pointer. If it's a null pointer, you fail, and you sort of bail out. But bailing out is actually not that sort of straightforward. The process might actually have allocated memory already. You need to get rid of that. You may have done some partial disk operations, like for example, if you do a multi-step file system operation, maybe you have done some of it, but not all of it. You have to bail out of that. And so it turns out to actually get it's very hard to get it right. And sort of interesting, when digging into this and trying to think about like how to solve this problem, Linux sort of uses both of these solutions, and both actually have trouble or problems. And indeed, kernel developers actually have difficulty to actually get this all straight. If you're interested in this and you want to see some interesting discussion about this, Google for too small to fail. And then, there's a little article that talks about some of these complications, of freeing memory or waiting in the allocator, and the problem that can cause. Now, it turns out for us, so Strawman 2 would be sort of the solution that you could imagine doing. But for us, just as mentioned earlier, it's just, for Biscuit, it was not possible because new just cannot return, cannot fail. It just always succeeds. So we got to arrange in some way that this cannot happen. Plus, neither of these two solutions are actually particularly ideal. So we wanted to come up with something that was potentially better. Any questions so far about the setup around heap exhaustion before I talk about how the way Biscuit does it? Does this problem make sense? I will interpret the silence as yes, and then keep going, but feel free to interrupt anytime. Okay, so what is the Biscuit solution? At a high level, the Biscuit solution is almost straightforward. What Biscuit does, when you execute a system call, like say read or fork, before jumping actually into the fork system call, like right at the beginning of the fork system call, if you will, like in the system call dispatcher in x86, then first thing it does, actually, it calls reserve. And it basically reserves enough memory to be able to execute the system call. So it reserves free memory enough that it can actually, whatever amount of memory that actually the system call needs, the reservation will be big enough that actually it will succeed. So once the system call goes off and it's actually successful in reserving memory, it will actually run all the way through, and we're never with the problem that there won't be enough memory or heap exhaustion. And if there's not enough memory at the point you want to do the reservation, then basically it just waits here. But at the beginning of the system call doesn't hold any locks. It doesn't hold any resources yet. So it actually is perfectly fine. It waits there. So there's no risk of deadlock. And while it's waiting, it can, of course, it can call, the kernel can actually evict caches, to try to reduce basically free up heap space. Maybe, as you've seen, maybe kill a process to force, memory to actually be freed. And then once, memory is available and the kernel decides, well, I can meet the reservation, then it will let the system call basically goes off and runs and basically executes, whatever needs to be done. And then at the very end, when the system call is done, it's just like, okay, I'm done. And all the memory that was reserved basically goes back to the pool available for subsequent system calls. And so there's a couple nice properties about these particular solutions. There's no checks necessary in the kernel itself, right? Like you never have to check, whether the memory allocation can fail, which is particularly in our case good because, in Go they can't fail. There's no error handling code necessary at all. And there's no risk for deadlock because you're avoiding in the very beginning when you actually hold no locks. Of course, this is all wonderful and well. The only thing is like how there's a challenge, of course, how you do the reservation. How do you compute, how much memory a system call might need to execute it. And so that was sort of a puzzle. And it's important that the amount you reserve, one you could do is like you can reserve like half of memory or something like that, like some ridiculous amount of memory for every system call. But that means you limit the number of system calls you can execute concurrently. So you want to sort of do a pretty good job at actually computing a bound of the amount of memory that the system call might need. So the way we ended up doing this and turned out like sort of the high level language helped us here. It turned out like Go is actually pretty easy to statically analyze. In fact, the Go runtime and the Go infrastructure ecosystem comes with a whole bunch of packages to analyze Go code. And we use those packages basically to compute the amount of memory that the system call needs. So you can think about the system, let's say like, you have the read system call, right? We can look at the call graph of the system call, calls the function f, calls the function g, calls the function h, or blah, blah, blah. It might continue a whole bunch. And then, at the end of the system call, sort of unwinds the stack again and then goes back to and returns to user space. And basically what we can do is allocate, or figure out like what the maximum depth, of this call graph is at any particular time. And then basically for that maximum depth, compute, how much, live memory each of these, functions need. So like if this function calls a new, that'll allocate some memory. We know what kind of objects there are. It's a high level language, so we can compute what the size of that object is. We can just add them up. And that gives us some number S that says like the total amount of memory or the maximum amount of memory that it can be live at any particular point in time for that call graph. And the reason is, it's slightly tricky. It's not as simple as this because, for example, a function h, might allocate some memory and then pass it back, to g. And so, h finishes, but g actually, gets the memory that h is allocated. And this is called escaping. The memory escapes from H to G. And it turns out there are standard algorithms for doing sort of this escape analysis to determine which variables escape to the callers. And in that case, basically whatever memory was allocated by H and that is still alive, we have to add it, to whatever G is. So, it has to be added into S.
A quick question about this. So let's assume we're in some function. Like depending on different workloads that the function is expected to have, there might be different memory amounts allocated. So what is there like a worst case memory allocation process?
Yeah, that's basically it. It's sort of a conservative scheme, correct? I mean, we compute the tool computes basically the worst possible depth of function calls. And for that, in the worst case, it analyzes how much memory that read system call might need. In practice, it might mean the system call might need a lot less. But to be conservative, we have to allocate we plan for the worst case. And so it's come to a couple important points here because some system calls, for example, execute a for loop that's dependent on an argument to the system call. Right, and so you can't actually statically figure out what the bound is. And so in a number of cases, we annotated the code to say like, well, this is the maximum bound of this loop, and you can assume it's no more than that, and use that to actually compute this number S. Similarly, for example, if you have a recursive function, who knows how deep the recursion is, right? And that might also be dependent on a dynamic variable or an argument to a system call. And in fact, we tweak Biscuit in some places to basically avoid recursive function calls. So that actually was possible to do this, to do this kind of analysis. And so this kind of analysis is not for free. It's not completely automatic. It takes a couple of days of work, for, in this case, Cody to go through, look at all these loops and annotate. There are a couple other sort of Go specific issues that you have to deal with. Slices, they might double in size if you add an element to the slice. And so we annotate the slices with some maximum capacity. But it's all sort of doable. So a couple of days of work and, using this tool, then you can sort of get a number out that is reasonable good in terms of, computing a maximum amount of memory that a particular system call needs. And so this is basically how Biscuit solves this particular problem.
Oh, sorry. What else are people using this tool for? Like they're not building a kernel. What are they using it for?
Well, for the static analysis packages,
Yeah.
The Go compiler internally uses it for all kinds of optimizations, and do static analysis on the Go code to figure out like the best way to compile it.
I see. Okay. Thank you.
And so this is one of the cool things about it. Just as a package, that the compiler happens to use, but we could use it too. You'll see later on, and we also use it for a couple other features. It's very convenient to have. Okay.
Thank you.
Okay, in terms of the implementation, Biscuit was basically very similar to other kernels, or like, in x86, except, more high performance. What we adopted many of the optimizations or cleverness that the Linux kernel has, at least for the system calls that we were trying to implement. We use large pages for kernel text, to avoid, TLB costs. We have per CPU NIC transmit queues, so to avoid synchronization between cores. We have an RCU, and we'll talk a little bit more about the directory cache. That is basically lock-free or read-lock-free directory cache. At the end of the semester, we'll talk about RCU in more detail, but Biscuit has it too. Sort of the usual type of optimizations that actually you need to get done to get high performance. And the main lesson I think we learned is that Go was not standing in the way of implementing these optimizations. This optimization could be that were implemented in C and Linux. We basically implemented the same optimization, but we implemented them in Go. And so the language itself is not a hurdle or a problem. In fact, it's completely conducive to actually implementing these optimizations. There was a lot of work to implement these optimizations, but that was irrespective of the language. Okay, so that brings me sort of to the evaluation, which is really what the motivation of the whole paper was, which is like trying to get a handle on the benefits and the costs of high-level language. So basically, the evaluation is sort of split in two parts: first talking about the benefits, and then talking about the costs. So, sort of three questions. First of all, there's a question like, did we cheat? Maybe we avoided all the expensive high-level language features that Go offers. The second question, of course, does the high-level language simplify the Biscuit code, and would it prevent some of these exploits that I mentioned earlier on in the lecture? So first, despite the use high-level language features, we just wanted to see whether we were sort of similar in terms of other big Go projects in terms of language features, so that we could say like, well, the kernel seems to be doing sort of roughly the same, taking advantage of the same features in sort of similar ways. So we used actually the same static analysis tool or package to basically analyze a whole bunch of two big pieces of Go software that are in GitHub. There are millions of lines of code. One is the Go runtime itself and all its packages, and the system called Moby. And then we just basically plotted for sort of the number of high-level language features, how many times they were used per 1,000 lines. And so this graph shows that. So here sort of on the x-axis are the language features. Basically allocations correspond to calling new, and sort of this corresponds to memory that it will be dynamically allocated by the garbage collector. Maps are like hash tables. Slices are dynamic arrays. Here's the channels synchronization. As you can see, we use them very, very littly, but so does the Go runtime and Moby. Clearly, the feature that we liked most was multifunction return. So being able to return multiple values. We use closures. We didn't use finalizer. We used defer a little bit. There's a bunch of Go routines that we do create. We use interfaces. Type assertions to convert from one type to another in a type-safe manner, and importing many packages. So the kernel itself is built out of many packages and not like sort of one big single program. So if you look at this, some features, Biscuit uses less than Golang and Moby, and sometimes, Biscuit uses some features more, or roughly in the, not in any sort of distinctly different way. So the main conclusion from this is, Biscuit uses the high-level language features that actually Go offers and doesn't sidestep them to basically get good performance. Okay.
I have a question.
Yeah.
How did you, how were you able to count all of this? Did you use the static analysis tool?
Yeah, you basically use the static analysis package, and then wrote a little program that uses the static analysis package to go over every statement in these programs and look at what kind of type of statement it is. And then, or you get the arguments and see how the arguments are being used, and that gives you a sense about how that allows you to count these features.
Okay.
Okay, so the next thing is a little bit subjective. The high level and simplified Biscuit code. I think in general it did, and I'll we'll argue one or two examples explicitly, but not having the GC allocation is actually very nice. And maybe I can make the point, like if you think about XV6 or like you do an exit, on a point of exit, there's a lot of data structures that need to be freed or returned to the kernel, so that later process can use. Using the garbage collector is really easy. The garbage collector takes care of all of it. You don't really have to do much. So if you allocate, free an address space, the VMAs that correspond to that address space will be automatically freed by the garbage collector too. Just that is just simple. As I mentioned earlier, the multi-return values were really nice in terms of programming style. Closures were nice. Maps were great. You don't have to. Many places, XV6, for example, looks up something in a linear fashion. But if you have hash tables or maps as a first-class object or abstraction in the programming language, you would never do that. Right? Just sort of write you just use a map, and the runtime will take care of doing everything efficiently. So in effect, I think qualitatively, it feels you get simpler code. But as clearly qualitatively, just to give a little bit more of a concrete example where it really, where sort of a high-level language, a particular garbage collector shines, is when there's a lot of concurrency between when there's concurrency between threads and the threads actually share a particular shared data item. And so, for example, here's the sort of simplest case, where you can boil down this question to. Let's say you allocate some dynamically an object like a buffer. You fork a thread, and that processes that buffer, and there's another thread that also processes that buffer and does something to this buffer. And when both threads are done, the buffer needs to be freed so that it can be used for later, later kernel operations. And the question is like, who should do this? Who's in charge? And there's a little bit difficult to coordinate in C because you have to have some way of deciding that actually the buffer is actually not being used. If you use a garbage collector, there's nothing to decide. Basically both threads run when they're done with the buffer. No thread is pointing to that buffer anymore. The garbage collector, will trace, starting from the thread stacks, and will never, and will not account that buffer in any of the thread stacks, and therefore the garbage collector will free, the memory at some point later. And so in garbage collector language, you just don't have to think about this problem at all. One way you could try to solve this problem in a programming language like C is you maybe could put reference counts on the objects. The reference counts, of course, have to be protected, by locks perhaps or by some atomic operations. And then when the reference count reaches 0, then you can dereference it. And it turns out locks and reference counts are actually slightly expensive. If you want a high performance, concurrency and scale up to a large number of cores, and then that actually can be a bottleneck. And we'll see that later in a couple of weeks. We'll read a paper that actually talks about this very explicitly. And so people tend to, if you want to do a high performance and get good parallelism, people tend to avoid them. And in fact, in particular, the scenario that we try to avoid them is like in ReadLock. You would like to make at least reading sort of lock free, so you don't have to pay the cost. And so, for example, here's a code fragment that would do that. Here we have a get function that basically reads the head of a queue and returns the whatever is at the head of the queue, and does it basically in a lock-free manner. It uses an atomic load to actually read the head, but it doesn't actually take a lock out. Then the writer does take locks out. So this is like lock-free. But the writer is not lock-free. This is a very common style in the Linux kernel. And so the writer actually, takes out the lock, whatever, looks at the head, maybe this is the pop function, and it pops up the head from the queue. And then, in principle, you could reuse it and then unlocks, or then you could free the head. Now, again, in C, that's a little bit difficult. When do you actually free the head? Because it could be the case that some other concurrent thread that just before you did this atomic store, this guy actually came through and basically got a pointer to that particular object. So once you're done with this atomic store, you can't actually free the pointer because could be another thread that actually has a pointer to it. And if you free it right here, you could actually have a use after free bug. And so we'll see in a couple of lectures. The Linux kernel has a very clever solution for this, which is called read copy update, or RCU. And basically what it does is it defers freeing of memory until it really knows it's safe. And it has a very clever scheme to actually decide when it's safe. But that scheme does come with comes with restrictions, and programmers actually have to obey some set of rules that you must follow for sort of RCU critical sections, as they're called. For example, you can't go to sleep in an RCU critical section or schedule. And so it turns out that, although, the Linux kernel uses this extremely successful, it's a bit error prone, and, it requires careful program to get it right. And in the case of the garbage collector language, like, Go, this is again, is like a non-issue because the garbage collector will actually determine when actually something is not in use anymore, and then only then free it. And so there's nothing really, there's no restrictions on the programmer, it's just taken care of by the garbage collector. So that's sort of an example of, where sort of, more maybe quantitatively or more, explicit, you can see sort of the advantage of a garbage collector language. Okay, in terms of the CVEs, I sort of mentioned this already. We went through all these CVEs and, sort of inspected them manually, and then tried to decide whether to actually go with fix the problem. For 11 of them, we couldn't figure out, we looked at the fix, the patch that addresses the CVE. We couldn't really figure out like what the outcome in Go would like, or how it would manifest, or how it would change. We could see how we implemented the fix, but we couldn't decide whether it actually Go would have avoided the problem or not. There were a number of logic bugs in these CVEs, and so presumably, in Go you would make the same logic bug as in C, and the outcome would be the same. But then, there were about 40 memory safety bugs, use after free or double freeze or out of bounds, and in 8 of these, you just disappear because the garbage collector takes care of them, as I sort of described in the last couple of slides. And in 32 cases, we Go would have generated panic because you, for example, would go outside of an array bound. And of course, panic is not good. The kernel crashes, but it's probably better than a security exploit. And so, so in 40 cases, basically the high-level language helped us. Okay, so that's the quality, sort of the benefits. So now I want to talk a little bit about the performance cost with the high-level language tags. But before doing that, let me ask if there's any more questions. Okay, I'm going to go through them. I'm not sure we'll make it through all 6 because I want to reserve a couple minutes at least at the end, to come back to the starting point of the lecture, the base question. So the setup in terms of experiments, the Biscuit runs on raw hardware. So these experiments are on little physical machines, not on top of QEMU. It's a 4-core, 2.8 gigahertz Intel processor, 16 gigabyte RAM, but hyperthread's disabled. We use 3 applications: a web server, a key value store, and a mail server benchmark. And all of these applications stress the kernel intensively. So they execute system calls, and the kernel must do a lot of work. And you can see that because most of the time actually in these applications is spent in the kernel. So first question is like, is Linux even, or is Biscuit even in the neighborhood of production quality kernel or industrial quality kernel? And so what we did, we compared the apps through Biscuit and Linux. For Linux, we used 4.9 Linux. That's a little bit out of date now because the papers, of course, are a couple of years old again. But of course, when we in Linux, we had to disable all kinds of features that Biscuit uses or doesn't provide. I mean, so like page table isolation, repliline, all kinds of long list of features that actually Biscuit doesn't provide, nor x86 provides, and we disabled them in Linux to make the comparison as fair as possible. And of course, there's some features are hard to disable, and we're not able to disable those. But we try to get as close as possible, and then we measured basically the throughput. And as you can see, the Biscuit is almost always slower. It's always slower than Linux. For Mailbench, it's about whatever 10%. On NGX, it's a little bit more. Redis is a little bit of 10-15%. But you should just use these numbers with a very grain of salt, right? Because they're not identical, and it's not an apples to apples comparison. But they're like 2 sort of first order they're roughly in the same ballpark at least. They're not like 2x, 3x, 4x, or 10x off. And so, maybe it is worthwhile to actually, be able to do and actually, to draw some conclusions out of it. So, so then we sort of looked at we basically profiled the code and tried to bucket, the cycles that were spent by the code. And in particular, we were looking at which cycles were actually in the garbage collector, which cycles were actually in the prologue of function calls, and the prologue actually in Go does a bunch of work, to ensure that the stack is large enough so you don't run off the stack. Write barrier cycles. This is actually when in garbage collection mode, the garbage collector turns on write barriers to basically track pointers between different spaces. And the safety cycles, which are safety cycles, are the cycles spent on array bound checks and things like that, and null pointer checks. And so if you look at these applications, here are the numbers. So 3% of the execution time was actually spent in sort of GC cycles, and I'll talk a little bit about why that's low. But there is the case that the garbage collector was running while running these applications. So it's not the case that we measured the applications. We give it so much memory that it just could run without actually running the garbage collector. Surprisingly, actually, the prologue cycles turn out to be the highest, and this is basically the way the scheme that they were using that time for checking whether the kernel stack or the stack of a thread needed to, or Go routine needed to be grown or not. And this is something that actually the Go designers at that point in thought that it's probably easy to get lower. Very little time actually in the barriers, and so 2 to 3% in the safety cycles. And so in some sense, this is good news. Not the tax is not gigantic. Of course, this number could be much higher because this is completely dependent on how big the heap is, or how big the live number of live objects is, because the garbage collector will have to trace all the live objects to actually determine which objects are not live. And so if there's a lot of live objects, the garbage collector will have to trace more objects. And so this is completely sort of linear with the number of live objects. So we did some other experiments. We zoom ahead a little bit, where we basically allocated a ton of live data, like a 2 million V nodes. Think about this as 2 million I nodes, and then freed the amount of sort of headroom, or change the amount of headroom that the garbage collector has, for free memory, and then and then measure the cost. So this is the table here. So we have 640 megabytes of live data, and then we run it with different memory sizes. And so in one case, there's 320 megabytes of data, so the ratio of live to free is 2. And you see that in that case, Go doesn't do a great implementation of Sears overhead for garbage collector, because the garbage collector needs to run a lot, because it doesn't have much headroom. But if the free memory is about twice, you could buy enough memory that the free memory is twice, that of the live memory, then the garbage collection overhead is not actually that crazy. It's in the 9% range. So basically, to keep the GC overhead sort of roughly around below 10%, you need about 3 times the heap size in terms of physical memory. Any questions about this?
I had a question about the write barriers.
Yeah.
What are those? Is it you set some permissions?
Okay, no, it's not. So I don't know if you remember the lecture from a little while ago, the Appel and Leap paper where we talked about the to and from spaces, and when the garbage collector runs, then you have to check whether the pointer's in the from space, right? Because if it's in the from space, you have to copy it. And basically, the write barrier is very similar. That is the same sort of type idea where you need to check every pointer to see if it actually points in the space that actually you need to garbage collect. And that's a write barrier.
Sorry, so the free memory, what is it exactly? How does it work that the live is more than free?
Okay, so you buy some amount of memory, and live memory is actually memory that was used by these V nodes. And then there was another 320 megabyte that was just free. And so when this application allocated more, V nodes, they first came out of the free memory until the free memory was full, of course, and then concurrently the garbage collector was running. And so we run it in like 3 configurations. And in one configuration, basically the amount of free memory is twice as the sort of the heap live memory. And so that means that the garbage collector has a lot of sort of headroom to do sort of concurrently while running with the application. And if there's a lot of headroom, in this case for a free memory, then the garbage collection overheads are not that high, or they're around 10% instead of 34%.
Okay, I see. Thank you.
You think about it as like there's a little bit of slack, sort of for the garbage collector to do its work.
Right. I thought that it's like total 320, and I was confused.
No,
Okay,
the total is 320 plus 640, and
Right.
the last line is 640 plus 1280.
Okay, thank you.
I'm just going to skip this. Actually, let me talk a little bit of pauses. This is the Go garbage collector is a concurrent garbage collector, and with short pauses, stops the world for a very short period of time, basically to enable write barriers, and then basically the application keep on running while the garbage collector does its work. And it's incremental, as like the one that we discussed a couple of weeks ago, where basically every call to new does a little bit of garbage collection work. And so every time that you do a little bit of garbage collection work, there's some delay that's being caused, correct? And so we measured, we took one application and looked at the sort of the maximum pause time. So the maximum time that an application could be stopped, because the garbage collector needs to do some work. And it turned out to be, the max single pause, was 150 microseconds. That's in the case of the web server that was using the TCP stack, and basically a large part of the TCP connection table needed to be marked, before continuing, and that took 150 microseconds. The maximum total pause time for a single NGX or an HTTP request is the sum of a number of single pauses, and the maximum pause time in total for a single request was 582 microseconds. So basically, when the request comes into the machine, during there was a total delay of 582 microseconds to actually execute that request. And it just happened very, very seldom. Only 0.3% of the requested times actually had a delay of more than 100 microseconds. And so that's not good if you're trying to achieve like an SLA or where basically the longest time a request takes is small. But if you look at Google papers about like in the tailored scale, like how long the longest request takes, they're talking about in the order of tens of milliseconds or milliseconds to 10 milliseconds. And so probably the programs that these particular programs that actually have a pause time, a maximum pause time of 582 microseconds is sort of within the budget. It's not ideal, but it's not crazy. And so that basically says that actually what this basically says that the Go designers did actually a terribly good job of actually implementing their garbage collector, or an impressively good job. And this is one of the things that we've noticed while doing this project. Like every time we upgraded the Go runtime to the next runtime, it came with a better garbage collector, and actually these numbers got better and better. Okay, one more sort of technical detail that I want to go over. So far, like the first comparison between Linux and Biscuit, it's not really fair, because Biscuit and Linux implement slightly different features. So we did one more experiment where we basically tried to code up 2 kernel paths completely identical, both in Linux and in like in C and in Go. And so we looked at the code path and sort of verified that basically, it implements exactly the same thing. And we looked at the assembly instructions to really see what the differences are. There are going to be some differences, correct? Because Go is going to pay these safety checks. But like just in terms of basic operation, that at least the code paths are sort of identical in terms of functionality. And we did that for 2 code paths. This is difficult to do. It's a painstaking job. We did it for 2, or Cody did it actually for 2. And then we compared them. And so here's the results from one of them. This is a pipe ping pong, sort of test. You ping pong a byte across a pipe. And we just looked at the code path through the kernel to actually get that byte from one end to the pipe to the other end to the pipe. The total amount of code in Go is like, this is 1,000 lines of code. In C, it's 1.8 thousand lines of code. There's no allocation, no GC, so those things are just differ. We also looked at like the runtime, like where's the most time spent, and in both code paths, the same top 10 instructions showed up. So we sort of have some confidence that the code paths really are close as you can get to make them similar. And then we looked at basically the amount of operations you can do per second. And as you see here, basically, the Go is a little bit slower than the C implementation, and the ratio is about 15% slower. And that's sort of, if you look at the prologue safety checks, these are all the instructions that the C code does not have to execute. They turn out to be sort of 16% more assembly instructions, and so that sort of roughly sort of makes sense. So the main conclusion is Go is slower, but pretty competitive. Not ridiculously slower, and that seems in line with the early results of where we did this Linux to Biscuit comparisons directly. Okay, so let me zoom a little bit further. Let me skip this because I want to talk a little bit about this sort of the question that we asked in the beginning, whether should one use a high-level language for a new kernel? And maybe like, instead of answering, I have some thoughts about this here on this slide, there were some conclusion that we draw, and it's not a crisp conclusion, there's some considerations. So maybe to take a step back, it's just like ask yourself the question, like, what would you have preferred? Would you have preferred to write, x86 and the labs in C, or would you have preferred to use a high-level language, for example, like Go? And particularly in answering this question, what kind of bugs would you have avoided? And maybe you have had some time during this lecture to think about like what bugs you had. And I would love to hear, what you experienced, how you think switching to a high-level language would have changed your experience. Or if you have any thoughts on this question at all. So let me pause here for a little bit so you can think about this and maybe chime in.
I have had a couple of times when I did the thing where I create an object in a function and then I return a pointer to it, and then I do stuff with a pointer, and then I realize that the object is gone.
Yeah, so this is a classic example of a sort of use after free case, correct?
Yeah. The second time I realized it faster than the first time.
That's definitely true. So we've seen it a couple of times in those bugs, you get better at them. Any other thoughts on this? Other experiences that people have had? Think about your worst bugs, or the bugs that took the most time. Would a high-level language would have helped?
I think it definitely, like some of the bugs were absolutely terrible to deal with, but at the same time, like in this context, I definitely appreciated having to work with such a low-level language as C, because it helped me to really gain a very like a deep understanding of what's actually going on inside the operating system, like how it's working with memory. Like it's definitely refreshing to like not have all of that abstracted away and to actually see exactly what's going on.
Mm-hmm. Yeah, that makes a lot of sense. Any other people have opinions on this?
I think I also made a lot of bugs in which I was writing after the end of a string or something like that, but then I wasn't getting any useful feedback about it, and then very strange things happened that I couldn't explain. So yeah,
I bet it showed up in lab 1, where there was a bunch of strings operations, like when you're parsing directories and things like that.
It showed up in multiple apps.
Okay, good. Yeah, no, I'm not surprised. Okay, that's a great example. Like, it's very nice to actually have real string objects.
One thing on my end is that I found myself lacking whenever I needed something like a map, and
Right.
I cringed every time I needed to do a for loop over something and then find.
Yeah.
However, I will say, like, coming from a high-level programming background, This was my first real exposure to something like C. So going off of Noah's point, it kind of helped me to understand really what it means that like this code that I'm writing is actually running on the CPU and everything is from the perspective of the CPU.
Mm-hmm. Yeah. Any other thoughts?
Oh, I actually remember it was specifically the difference between safe string copy or just string copy. One of them was was using the null terminator, and
Yeah.
that was
Yep. Yeah, the common C bug. Well, so first of all, thanks for the input. Of course, we're not going to change x86 to Go or any high-level language, exactly for the reasons that I think a number of you, like Noah and Amir, actually mentioned. Go still hides too much, and in this particular class, the whole purpose is really trying to understand everything sort of between the CPU and the system call interface. And so, for example, Go, of course, hides threads, and we don't want to hide that. We want to explain to you actually how threads are implemented, and so we would not want to hide this from you. So certainly, future years, of x86 or this class will keep on using C. But like if you implement a new kernel, and the goal is not educating students about kernels, but the goal is to write like a sort of a safe, high performance kernel. There's sort of some things you can conclude from the study that we've done, right? If memory or if performance is really paramount, you can't like sacrifice 50%, then you should probably use C. If you want to minimize memory use, you probably should use C too. If safety is important or security is important, then probably the high-level language is the way to go. And probably in many cases, performance is merely important as opposed to absolute, paramount. And in many cases, I think, using high-level languages is a perfectly reasonable thing to do for a kernel. And probably one thing I've learned, or probably, that Cody, Robin, and I learned from this whole project is like, whatever, programming language is a programming language, and you can use it to build kernels, you can build user applications. There's not really standing anything in the way. Okay, I think it's time to wrap up. But if you have any more questions, feel free to hang around and ask them. If you have to go somewhere else, good luck with finishing the MAB lab. And for those of you who are leaving campus for Thanksgiving, safe travels. And hope to see you after Thanksgiving in Monday's lecture after Thanksgiving.
Thank you.
I was curious, how did you implement it? Like you said, you were doing that just on the hardware. So like when you start out, how do you start out?
There's basically a little bit of shim code that sets up enough of the hardware so that when Biscuit, asks for, or when the Go function, the Go runtime asks for memory for the heap, that we can actually respond. And that was one of the main things that actually the Go runtime actually relies on.
Right. I guess it was like you said that you didn't use a virtual machine for that. So
yeah, we did, of course. We developed.
Oh, okay.
Most of the development was on QEMU. And of course, in the end, we actually had to get it running on the raw hardware. That also cost us a bunch of problems, because the bootloaders are different. There's a bunch of boot code that you actually need to write that you don't have to write if you run it on QEMU, and that kind of stuff. But most of the development is all done on QEMU. In fact, if you want to, I can show you running Biscuit on QEMU, and it looks very similar to x86. The only thing it does is like, shows your prompt. There's no window system, nothing like that.
Okay, I see. So like what happens if you make a mistake in the boot code?
It doesn't boot. Basically nothing happens. It's completely nothing.
How do you know?
You will know because okay. What will happen is, of course, you don't see a print statement. Like in x86, like the first thing we print is like x36 hello or something, or x36 is booting. You won't see anything like that, and so you will see nothing. And then you'll have to track down and guess what the problem might be.
Okay, so you do it by looking?
Okay, so a little bit. You can write synchronously to the UART. You can put like stupid little, characters, and you see put them in random places in the code and hope that you see something.
This is interesting. Thank you.
So I wanted to ask, when so I know like you implemented the Go, some of the calls the Go runtime would make that you cannot make because you're implementing the kernel itself. Is there any, like, did you just implement just all of that in assembly, or did you say, okay, like some of this we can still do in Go, like we can bring Go a bit closer and then do assembly only what's necessary? Or did you just say like once the Go runtime ends, like that's assembly?
That's where the 1,500 lines of assembly came from in Biscuit. That is basically the code to sort of get everything ready to be actually able to run the Go runtime. Now, some of that we could have implemented in C, but we didn't want to do that because we didn't want to use any C, so we wrote in assembly. And many of it actually requires assembly because it's in the booting part.
Right, but I guess some of the part that's not the boot. So I'm I know that some just you cannot avoid some boot code in assembly. But could you have transformed some of the assembly to Go, or did you go to the absolute max?
No, we did. Wrote a whole bunch of Go that basically runs very early on. And some of the Go is quite careful. It doesn't do any memory allocations.
That makes sense.
We try to write as much as possible in Go. I can I have to look at the code exactly, to be able to answer your question specifically. You can look at the Git repo, but we try to write everything in Go.
And then one like kind of unrelated small question I had. What does Go do with its Go routines that makes it possible to run like hundreds, thousands of them? Because you cannot just spin up 100,000 P threads, right?
Yeah, it depends. Okay, so longer answer. The main issue is that you need to allocate a stack, and the Go runtime actually allocates stacks incrementally, and so grows them dynamically as you run your Go routine. This is where this prolog code is for. When you make a function call, you see if there's enough space to actually make the function call, and if not, it will grow the stack dynamically for you. And often in pthreads implementations, allocating threads is a little bit more heavyweight because actually, for example, in Linux, basically a corresponding kernel thread is actually allocated too, and they tend to be more heavyweight then.
I see. Is the scheduling of all the Go routines done completely in user space,
yes,
or does it help itself with some kernel stuff?
It is mostly done in user space. So the Go runtime allocates a bunch of kernel threads. They call them, I think, M threads, and on top of that, it implements the Go routines.
So it has like a couple kernel threads that it shares to all Go routines based on which one's running.
Yes.
Oh, that makes a lot of sense. Yeah. Is there like any C++ equivalent? Like, could you do something like that to save some memory?
Yeah, people have done, implemented like high performance, so C libraries or thread libraries that where you can create like thousands of threads or millions of threads, to with similar style.
Okay, you guys have a good break. Gotta head out.
You too.
See you next week. Oh, 2 weeks.
You too.
Yeah,
Go ahead, Brandon.
Oh, go ahead.
Okay, sorry. So I had a maybe basic question about the shims, and I think also maybe because I'm just not familiar with kind of specifically what like a runtime is. And I guess like my confusion comes from the fact that like from a mental model of how like x86 and C works is that C is a compiled language, and so it goes directly to assembly or machine code. And so it kind of just runs on the CPU. And so I guess like there is no need for a shim for like an x86 OS. But I guess my understanding is Go is also a compiled language, so it also goes to like assembly. So why is there a need for like a shim in this case? Like why is there a shim for like XV6, or what is different here, and like why are there things that can't just be done on the CPU?
Yeah, really great question. So I think the answer to your question is that the Go runtime provides all kinds of features that you don't have, correct, in when you're running C in XV6. So the Go runtime provides threads. Go runtime provides scheduler. The Go runtime provides hash tables. The Go runtime provides a garbage collector that actually needs to run at runtime, right? And there's no garbage collector in XV6, and we implement the threads. And for example, to support the garbage collector, it needs a heap, for to allocate memory from. And so it asks the operating system, underlying operating system, please give me, some memory so I can use it as a heap. And basically, the shim layer implements exactly that kind of functionality that the Go runtime needs to do its job at runtime. Does that make sense?
I think, yeah, I guess I have it slightly makes sense. I guess like a follow-up question is, maybe this is a dumb question, but like can't we just compile the runtime down to machine code? Or
the runtime is compiled to run
okay,
machine code. So the runtime itself is also compiled, but it's like sort of part of the program that needs to run always when you're running Go code. It has to be there. Like even like C has a small runtime. If you think about we have like printf is part of the C runtime, or like string operations are part of the C runtime, right? And they're compiled too, but there's a bunch of like small number of functions that the C runtime has. But the runtime is so small compared to like the Go runtime that has to support many more features, because the programs, the Go programs rely on them.
I see. And I guess like the last question would maybe be is it kind of sounds like that in this case the Go runtime, or like actually the shim in this case, is almost taking on some of the functionality that would normally, like it's almost like it's like a mini, it's almost kind of like it's like a mini OS layer, like in terms that it's just like another layer that's performing some low-level system functionality.
Yeah.
Is that like reasonable?
Yeah. You can also think like maybe one way to think about it is XV6 also has a very minimal shim. Maybe like when it boots, correct, the first thing it does actually it allocates some stack so that you can actually call the C main function. And you can think about that little fragment of code, which is only a couple statements, as the shim layer for XV6. And once you're through that couple of instructions, you're actually in C code and everything is fine. And the shim layer for the Go runtime is slightly bigger because there's a bunch of more features that need to be set up before the Go runtime can actually happily execute.
Okay, yeah, that's helpful. That makes sense. Cool. Thank you.
You're welcome.
Happy Thanksgiving.
Yeah, you too.
Oh, I had a question about the ping pong program that I forgot to ask. So I remember we also did a ping pong program in one of the labs, and it was not 1,000 lines of code. Why is
because like lab one, I think are you referring to lab one where you do the ping pong of a byte across a pipe?
Yeah.
Okay, so that's the user side of the benchmark. The kernel side, correct, is the other side of it. And basically, what we did is implement the kernel paths in an identical manner.
Okay.
So like, you executing the start of the system call, or saving variables in the stack frame, calling into looking up the pipe, and then running maybe the scheduler to wake up, the receiver, and that whole code path, on the kernel side. We try to implement it identically in C and in Go.
Okay, I see.
But the benchmark is basically the same as your benchmark that you implemented actually in lab one, the user level side of it.
Right. Okay, that makes sense. So does that mean that I think that if you do that in XV6, it would be significantly less than 1,000 lines of code if you take all the kernel code that is.
So this is thousand lines of assembly instructions, correct? So I don't know. I will have to look at it, but you're gonna use the trap frame code, statistical dispatch, going to the FD layer, correct? The file descriptors, then a little bit of pipe code, then some copy in and copy out, then the scheduler, and then basically all and then bailing out again or returning.
Yeah, okay. That makes sense.
There's a,
So-
I don't know on the top of my head how much lines of code that is, but there's
Right.
there's quite a
Yeah,
bit
yeah.
going on.